AP Chemistry, Lesson 5, Discovering the Atom. So, an orbital, also called a shell, is an energy level at which electrons must stay. Electrons can pass from one orbital to another, but they can't stay for long periods in between orbitals. Niels Bohr came up with the idea of circular orbitals about 100 years ago. You will learn later that the shape of orbitals are more complex than this. Electrons in orbitals further from the nucleus have more energy. So the nucleus is pulling the electrons in. As they gain energy, they're able to move out away from the nucleus and into higher and higher energy levels. Orbitals can be compared to steps on a ladder. You can climb up or down steps on a ladder, but you can't stand in between steps on a ladder. In 1897, English physicist J.J. Thomson discovered the electron. Thomson placed a negative plate and a positive plate at opposite ends of a cathode ray tube, which caused a stream of electrons to move across the tube. By placing a magnet on the side of the tube, he caused the electrons to curve. And from this, he was able to determine the mass and charge on an electron. So there's the negatively charged plate. So remember, negative repels negative, so that means electrons are going to fly away from that plate. On the right is the positively charged plate, so electrons are going to be attracted to that plate. So you can that's actually a stream of electrons. That's not a graphic or just an illustration. That's actually a stream of electrons going across a tube. And when the magnet is placed on one side, it causes the electrons to change direction. In 1904, Thomson proposed a model of the atom that included electrons. At this time, that was the only one of the three particles that was known. He knew that there must be a positive charge to balance the negative charge of the electron. He believed that the positive charge was evenly distributed in a sphere with electrons spread around the sphere. So the model has electrons stuck in a positive sphere. This model became known as the Plum pudding model of the atom because it was a soft, solid sphere with chunks of electrons in it. So English plum pudding is what that stuff on the right is. It's kind of like a cake. And it has pieces of plum stuck in it. So that's the way he kind of envisioned the atom as looking like. In 1911, Ernst Rutherford performed his gold foil experiment. The experiment demonstrated two things. One, an atom has a solid nucleus, but that most of an atom is empty space. Rutherford shot alpha particles, positively charged, at a thin sheet of gold foil. If Thomson had been correct, the alpha particles would have shown small deflection. In other words, if the nucleus of an atom was soft, then those alpha particles would have been like bullets and just fired right through them. Maybe they deflect a little because there's a negative charge, there's some electrons in there, but they basically would have gone essentially straight. In fact, most showed no deflection and some actually bounced back. This indicated a solid nucleus surrounded by empty space. So Rutherford was very shocked by this, that some would actually bounce straight back at him. So this refuted Thomson's hypothesis that the atom was soft. Rutherford showed that it actually had to have a very hard nucleus to cause the alpha particles to bounce back. So if you imagine this is a close-up of what Rutherford was doing. So there's a positively charged alpha particle. So that one is not going near a nucleus, it's just going to fly straight through. Same with the one on the bottom. Most of them are going to miss the nucleus. Occasionally one will get close to the nucleus because the alpha particle is positively charged. What an alpha particle is it's 2 protons and 2 neutrons. So it's positively charged. Some are deflected by the positive charge of the gold nucleus, because the gold nucleus has protons as well. So it's going to cause the protons in the alpha particle to be repelled and push away. But occasionally a few hit it directly and bounced back. The discovery of the proton is credited to Ernest Rutherford, who proved that the nucleus of the hydrogen atom, i.e. the proton, is present in the nuclei of all other atoms in the year 1917. So everything we know about atoms really was discovered really within about 100 years or so. In 1932, English physicist James Chadwick discovered a particle that had the same mass as a proton but no electrical charge. This particle was called the neutron. Protons and neutrons each weigh about 1,820 times more than an electron. So if you put the nucleus of a helium atom floating above the middle of what used to be San Diego Stadium but is no more, and the stadium were the atom, the nucleus would be about 1 millimeter in diameter. The electrons would be in the upper level. Most of the volume of an atom is empty space. So there's the nucleus, but that's much larger than it would appear if you were looking from there. It would be a millimeter, is just tiny, very, very tiny. You wouldn't be able to see it from where that picture's taken from. And then the electrons would be in the upper deck. That's how far they'd be. So the vast majority of all atoms is empty space, which means the vast majority of all matter, which is made up of atoms, is empty space. The vast majority of your body is empty space. So if it's empty space, the question comes up, why can't you see through it? And the answer is because light waves require a certain amount of space to travel through. And if the amount of space is too small, light waves can't fit through it. And therefore, the empty spaces are so tiny that even though most of substances are empty space, light waves cannot travel through them. An isotope is an atom of the same element, but with a different number of neutrons. So this is where Dalton had it a little bit wrong when he said all the atoms of an element are the same. This is an example where you could have 2 carbon atoms, for example, but they could have different numbers of neutrons, and so they would be different, but they're still carbon. So a lithium-7 atom has 4 neutrons. So let's look at this diagram. It has 3 protons, and to balance that, it has 3 electrons. That's called electrically neutral. Same number of positives as negatives. And most lithium atoms, the vast majority, have 4 neutrons. Now here's a lithium-6 atom. It has 3 neutrons. So that's what's called the mass number. Those numbers there, the 7 means there's a total of 7 protons and neutrons, and the 6 on the one on the right means there's a total of 6 protons plus neutrons. The notation for an isotope is shown there. So you have the atomic symbol, and then up above you have the mass number. Down below you have the atomic number, and we're going to define those here coming up very shortly. Okay, so what the atomic number is, the number on the bottom, it's the number of protons. That's what defines an element. Lithium is lithium because it has 3 protons. It has to have 3 protons. However, it can have different numbers of neutrons. So therefore, there's a lithium-7, which has a total of 7 protons and neutrons, and a lithium-6, which has a total of 6 protons and neutrons. So it can have different number of neutrons, it's still lithium. The mass number, the number of a specific isotope, is on top, and the atomic number is the number on bottom. An alternate notation for an isotope is written as you see there. Another way an isotope can be expressed is shown here. The atomic symbol is followed by the mass number only. The assumption is that you know that lithium has to have 3 protons, so all they're giving you here is the mass number. An ion of an element is an atom that has a different number of electrons and protons. So here's an electrically neutral normal lithium atom. It has 3 protons and 3 electrons, so it's electrically balanced. An ionized lithium atom is shown on the right. It's lost an electron, and why and how that happens we'll talk about soon. So it has 3 protons and only 2 electrons. So it has a 1+ charge. It has a positive charge, a net positive charge of 1, because it has 1 more proton than electron, so that's called a 1+ charge. The lithium atom on the left has 3 protons and 3 electrons, so the charge is balanced, and the atom is electrically neutral. So that's a term to become familiar with, electrically neutral. It means it has the same number of protons as electrons. The lithium atom on the right has 3 protons and 2 electrons and is a positively charged ion. An anion is an atom that has more electrons than protons. This fluorine atom is an example of an anion. It has one more electron than proton. An anion has a negative charge. So if you count there the number of protons in the nucleus there, those red circles, there's 9 of those. And if you count the number of electrons in those 2 orbitals there, and you see this has a first orbital and a second orbital, there's 10 electrons total. So it has 1 more negative charge than positive charge, and that's called an anion. It's a negatively charged ion. So this grumpy guy is a negative antion. So that's how you can remember that, negative antion. All right? And that's the definition of anion. A cation is an atom that has more protons than electrons. This lithium ion is an example of a cation. It has 3 protons and 2 electrons, which gives it a positive charge. So this dude is a positive cat. So that smiling cat is the positive cat, so positive cation. The atomic mass of each proton and neutron is 1 atomic mass unit. That's basically our working definition for the mass of a proton or a neutron. It's just simply defined as they both have the same mass, close enough. Not exactly, but close enough. So we call that 1 atomic mass unit. An element's rounded atomic mass number tells us how many total protons and neutrons one atom of its most common isotope has. So you're going to see some examples of that. That last statement will make more sense. So 1 proton is 1 atomic mass unit. 1 neutron is 1 atomic mass unit. The technical definition of an atomic mass unit that it is equal to 1/12 the mass of a carbon-12 atom. The mass of a standard carbon atom with 6 protons and 6 neutrons. Now, why do they give you that technical definition and not just say 1 neutron? Because, as I said, a neutron really is slightly more massive than a proton, ever so slightly. So they decided to make an atomic mass unit kind of an average of the mass. If you take the mass of a carbon-12 atom, so it has 6 protons, it has 6 of the protons with their mass and 6 of the neutrons with their mass, which is just a little bit more, and you average it out, you'll come out with a number that's directly in the middle of the mass of a proton, mass of a neutron, and that's officially what an atomic mass unit is, technically. But for our purposes throughout this class in AP Chemistry, a 1 atomic mass unit is the mass of a proton or the mass of a neutron. We're going to treat them as though they're identical, as though they're equal. An AMU gives scientists a unit of measure for mass on the atomic scale. However, it's not practical for lab calculations. We simply don't have scales that can measure something that light with that little mass to it. So let's learn to read the periodic table and each of the entries on the periodic table. The number at the top is the atomic number. This is the number of protons that an element has. It is the number of protons that gives an element its identity. So remember that. It's protons, not neutrons or electrons, that define the element. Hydrogen must have one proton. So the atomic number is also the number of electrons that an element has in its electrically neutral state. Electrically neutral means that the number of protons and electrons are the same. Atomic number is also called Z number. We generally don't use that phrase a lot, but you can see it, and so become familiar with that Z number. The atomic symbol. This is the abbreviation for the element that is used in chemical equations. Atomic symbols are often based on Greek or Latin names, so the letters don't always seem to match the element name. The atomic name. This is the name of the element. Atomic names can vary by language. However, atomic symbols are universal across language. So, for example, in German, the word hydrogen is different. It's the German word for hydrogen. However, German chemists still use H as the abbreviation. The atomic mass. This is the average of the masses of all isotopes of an element. The atomic mass is the average mass of all isotopes for an element. This accounts for the decimal number. Example, if 50% of the isotopes of an element have a mass of 3 and 50% have a mass of 4, then the atomic mass would be, the atomic mass of that element would be 3.5. It would just be an average. So that's why atomic masses have decimal numbers. The rows in the periodic table are called periods, and the columns are called groups. Now, oftentimes we'll just call the rows rows and the columns columns, but you should be familiar with the term. Technically, a row that's going across is called a period, and a column, or that's going up and down, is called a group. So each period, each row, represents a new orbital. So the first row represents the first orbital. So hydrogen and helium have one orbital because they're in the first row. The second row represents the second orbital. So lithium all the way through neon over on the right has two orbitals. The third row represents a third orbital, the fourth row a fourth orbital, and so on down the periodic table. You're just adding orbitals. So that's starting to give you an explanation as to why the periodic table is shaped the way it is. Each group, each column, represents an additional valence electron. So what you're doing each time that you go from left to right across the periodic table, and this is only the representative elements. Remember, that's the first two columns and the last 6 columns. It does not include the transition metals. That's where it says no valence electrons. But every time you go from left to right, you're adding an electron to whatever that element's valence orbital is. So the first column, the 1A column, has one valence electron. So hydrogen has one orbital, that's its valence orbital, and in that orbital it has one valence electron. If you go over to the other side, and the first row is unique in this, helium has 2 valence electrons because it's the second element in its row. There's no elements in between hydrogen and helium in the first row. So it has 2 valence electrons. It also has 1 orbital, but it has 2 valence electrons. And you can see those are the only 2 elements in the first row. That means there are no more elements that have only 1 orbital. It's only hydrogen and helium. Okay, now the second column, with the exception of helium, the second column represents the second valence electron. So if you look at lithium, let's go down to the second orbital. If you look at lithium, it has 2 orbitals, and it has 1 electron in its second orbital. That's its valence orbital. Beryllium also has 2 orbitals, and it has 2 electrons in its outside or valence orbital. Now we skip across the transition metals and we go over to boron. Boron also has 2 orbitals, and it has 3 electrons in its outside or valence orbital. If we look at aluminum, let's go down a little lower. If we look at aluminum, aluminum is in the third row. It has 3 orbitals. It also has 3 electrons in its outer orbital. That would be its third orbital. Gallium, Ga, has 4 orbitals. It has 3 electrons in its outer orbital, its fourth orbital. So it's like a table where you cross-reference. Going down tells you how many orbitals. Going across tells you how many electrons are in the outermost orbital. And remember, these valence electrons are the ones that do all the chemical bonding. They're the ones that come in contact with the outside world and bond with other atoms. As we continue across, carbon. Carbon has 2 orbitals. It has 4 electrons in its valence orbital. Nitrogen, 2 orbitals, has 5 electrons. Oxygen has 6 electrons. Fluorine, 7. Finally, we get to neon that has 8. And that's at the end of the row. The valence orbitals can all hold 8 electrons, with the exception of the first orbital, which can hold 2. So you notice as you go down the periodic table, every row has 8 representative elements. And again, you don't include the transition metals, those light blue ones. So it has 8 representative elements, the 2 columns to the left and the 6 to the right. So every valence orbital, every outer orbital can hold up to 8 electrons, and then it's full. So now we're going to build an atom based on what you know. We're going to do a diagram of the atom. Okay, so we're going to take silicon. It's in the third row. And there's a few steps to this, and it just takes a little bit of practice. So let's look at what silicon has. It has an atomic number, or Z number, of 14. That means it has 14 protons. There's the atomic symbol as Si, and there's the name silicon. Now it has an atomic mass of 28.9. That's the average mass of all the isotopes of silicon. That is, there's different numbers of neutrons. There's different silicon atoms that have different numbers of neutrons. But the most common one is the silicon that has a mass number of 28. That has a mass number of 28. So that's why that number is closest. The closest whole number to 28.09 is 28. So most silicon atoms have a mass number of 28. That means they have 28 protons and neutrons added together. Okay, so let's take that information and let's build a diagram of a silicon atom. So silicon has an atomic number of 14. So it has 14 protons, and when all atoms are born, they are electrically neutral. They're electrically balanced. So that means it also has 14 electrons. So that number right there. So we're going to keep a scoreboard here of protons, electrons, neutrons, orbitals, and electrons in the valence orbital. So right now we've determined that there's 14 protons and 14 electrons. And we can go ahead, that rectangle represents our nucleus. It's drawn as a rectangle so as not to confuse it with orbitals, which will be more circular. Okay, and we're going to take those 14 electrons, we're going to put them off to the side right now. We're not going to place them. We're not quite ready to place them yet. Now we round the atomic mass to the nearest whole number. This is the mass of the most common isotope of silicon, which is Si-28. So the 28.09 implies that there's probably some silicon-29. That means it has an extra neutron. Maybe even a very tiny amount of Si-30. That would be 2 extra neutrons. But most of it, since it's closest to 28, is going to be silicon-28. So 14 protons. And now we're going to figure out how many neutrons. So first we're going to round that number to 28. So you see we just did that right there. And now we're going to do a little arithmetic. Now we can calculate the number of neutrons by subtracting the atomic number from the mass number. The mass number is the number of protons and neutrons, and that's 28. You minus the atomic number, which we know is the number of protons alone, and that's 14. And when you do that subtraction, you get the number of neutrons. 28 minus 14 is 14. Okay, so we can go ahead and place that number there. And we can also go ahead and place it in the nucleus. So the nucleus is taken care of. 14 protons, 14 neutrons in a silicon atom. A standard silicon atom, the most common isotope of silicon. So because silicon is in the third period, that is the third row, it has 3 orbitals. So everything you see covered in green there is going to have 3 orbitals. Everything there is in the third row. So we now know how many orbitals. So we're going to go ahead and place those orbitals. Okay, there's 1, there's 2, and there's 3. So there's the 3 orbitals. Now we place the electrons. The first orbital gets 2 electrons and then it's full. How do you know that? Because if you look at the first row, it only has 2 elements, hydrogen and helium. 1 electron, 2 electrons, and then it's full. So the first orbital is very close to the nucleus. It can't hold that many electrons. It's kind of small. So it gets 2 electrons, like that. Okay, the second orbital gets 8 electrons, then it's full. But watch how they're placed, and there's a reason why they're going to be placed this way, which you will learn. So yes, you could just draw 8 electrons around that second orbital, but watch specifically how I place them. By the way, there's the no vacancy sign for the first orbital. It's filled up. So here goes the second. I'm going to place 1 on the bottom. I'm going to spread the electrons out as much as possible around the sides of that circle until I've gone all the way around. There's 3, there's 4. At this point, the electrons must start pairing up. And we'll talk about why that is later, but just for right now, just accept that's the way it is. So there's the 5th. It pairs up with that electron down there, that electron on the bottom. The 6th pairs up with the electron over on the left. The 7th pairs up with the electron on top, and the 8th pairs up with the electron on the side. So that second orbital now has 8 electrons. That's all it can hold. How do you know that? Because the second row has 8 representative elements. So that now has a no vacancy sign. It can't hold any more electrons. So now we're ready to place the last 4, and we're going to place them the same way we did in the second orbital. So the first one's going to go down here, the second one's going to go over here, the third one is going to go up there, and the fourth one is going to go right there. All right? So those are the valence electrons. All right? We know that silicon has 4 valence electrons because it is the 4th element in the first row. Sodium is 1, magnesium is 2. Now you skip across and you got aluminum is 3, and silicon is number 4. So that's how you know how many valence electrons. And sometimes that's the only thing that you want to know, is the number of valence electrons, without having to draw this whole diagram. So that's how you can determine that. So that's it for silicon. That's how you diagram an atom. I'll have you practice that with some other atoms. But more importantly, it's teaching you how to read the periodic table, and it's giving you greater insight into why the periodic table has the shape that it does. So that takes care of that. You've gotten a little further knowledge about the atom. It's really important to understand it because it really is going to be the basis of all the chemistry that we talk about this semester. Okay, so we'll see you in the next lesson.